Welcome back to another episode of Dominic Does DIY. Don't forget to click subscribe and share, and thanks to all those that subscribed and repeat views. If there's something I can improve or something you'd like to see more of, let me know below in the comments. So today the boss comes in and says he needs a 2.5 volt reference with plus or minus 50 millivolts supplied by a 3-cell lithium battery pack. And don't worry about outrageous thermal requirements, room temperature is fine. He comes in with a box of random stuff he took from his kit. Looks like some leftovers from our Arduino starter kit. You think for a second and go to your lab and search for a single chip solution because you want to get back to your main project. After scouring the lab, you found some various different regulators, but unfortunately none that are adjustable to 2.5 volts with the voltage range requested. You go to the box of random stuff and start seeing what inventory you have to work with. After inspecting the box, the stuff you have to work with is one op amp, an LT6003, 3 Schottky diodes, a 1N914, and an assortment of resistors. The parameters of operation are you have to have a solid 2.5 volt reference with a wide input voltage range. The voltage range for a 3 lithium cell from low voltage to fully charged has a range of 9 volts to 12.6 volts. And since he just wants a voltage reference, we're talking low current, less than 5 milliamp drive. We would also like a buffered output so as the reference voltage itself is not affected by any additional circuitry. Pause the video now if you'd like to try and work this out yourself. Otherwise, I'll go over the solution shortly. Of course, as an engineer, you know that this is not the only solution that there is, but this is a solution that I am going to go over. So if you have another solution that you have found, go ahead and put it down in the comments. So I can take a look at it because I'd be interested to see some other solutions that you may come up with. So first thing we got to do is take a look at these components to understand what we're working with. So we'll start with the op amp first. So let's go ahead and grab the data sheet. Since this is a static application, we just have to verify a few things. We don't care about all the parameters like the switching frequency, slew rates, all that stuff is irrelevant with regards to an op amp. All we care about are a few of the operating points. So the first one we can find right in the main description here, it is a rail-to-rail input and output. So we don't have to worry about doing any kind of fancy offsets. In fact, if we go down to the offset voltage range, let's scroll down a little bit, and you can see even if we were taking into consideration the input offset voltage on the pins, it is only about 1 millivolt. 1 millivolt is inconsequential for what we are going to be doing. Actually, when we start getting into it, we'll see that what we're going to be looking at is upwards in the range of hundreds of millivolts. So 1 millivolt on this offset really doesn't matter, and it's inconsequential for this particular application. So we don't have to worry about it. So the other component besides the op amp was the 1N914 diode. And what we care about this one on is if we scroll down, we want to take a look at the forward voltage and versus the forward current versus forward voltage graphs. And we'll get into this later when we're actually designing it, but we're going to want to pay attention to these. But one thing you want to do just to notice right off the bat is, like most diodes, the forward voltage is dependent on the current, for one. This one is highly affected by it. And the other one is, you can see the temperature on this one. It also varies the current to voltage curve on it. So depending on if we're at minus 40, 25, or 65, depends on which curve and what our forward voltage is going to be. But since we're just dealing with room temperature, we'll only be caring about the 25C curve and line on this. So we'll be using these graphs primarily when we get to that stage. So first we'll just take a look at a simple voltage buffer. This is just a basic follower circuit for an op amp, but this will be able to meet our needs, right? We'll be able to have some sort of reference voltage, and it will be buffered on the output thanks to the op amp. So with the range of battery that we have to work with, remember it's from 9 volts to 12.6 volts, the nominal being 11.1, which is the 3.7 times 3. The resistors that were chosen were based on that. But let me break out my calculator that I use. So I have here my reference voltage, which I will be using in some of the formulas down here. So if I want to change my reference voltage, it can change some of the formulas. This is just listing what my battery voltage is for my own reference. But when I want to do my math on stuff, I'm using this cell right here, the VN cells here, in order to do all the math. So first things first, this is just a simple voltage divider. So we have our ground resistor, which I fixed at 10K. And then I want my 2.5 volts on the output at 11.1 volts. So you can see here, 11.1 volts. We calculate out the standard voltage divider formula. And we end up getting an R1 of 34.4. And when we have those two resistors, the voltage that we get on the output is 2.5 volts. And the minimum and max we get this min and the max, when you're doing engineering work, you always got to do tolerance stack ups. So that's what this 1% is for. So if you look at this formula right here, you may not be able to see it because it's really small. But right here, the formula is, it's just taking the nominal voltage and then minusing 1% and adding 1%. So it gives me my min and max in a lot. Like if I get 10,000 resistors, this will be the range of those resistors in a 1% roll. And then I can use those because basically the minimum voltage is going to be when I have the biggest ground resistor. The minimum voltage is going to be when I have the smallest ground resistor and the biggest R1 resistor. And the maximum one is going to be when I have the maximum ground resistor and the minimal R1 resistor. And so that's where we get the results of that. So just for the 11.1 volt reading, at nominal we'll have 2.5, but within the range of things, range of resistors that there are, we can go anywhere from 2.46 to 2.54. So now what I did is, using this formula, I can now take all these values, which you can see since this is for 11.1, going into my thing, I place that right there. And then if I cycle through these at 9 volts, you can see I got 2 to 2.06. And at 12.6 volts, I got 279 to 288. So for this simple voltage divider buffer, during the course of the discharge of the battery and the charging of the battery, in order to get 2.5 volts at nominal, we will go anywhere from 2.03 to 2.84 volts. So this does not meet the spec. This is not a good way to do it. I was just showing this for a quick, and if we had a fixed voltage where our input voltage was a set voltage and it was really tight, then this would be the easiest, fastest way to do it. But because we have to work between 9 and 12.6 volts, this is a very bad way to do it. So this isn't going to work well, but let us just see and confirm that this is what we expect to see in the simulation. So let's go and run the simulation on that one circuit. This time we're going to be doing DC sweeps. So this is V3. And you can see I'm starting at 9 volts, ending at 12.6 with a step of 0.1. So let's go ahead and run that. And it's going to run that step DC sweep on this V3 right here from 9 to 12.6. And you can see, just like my math predicted, we basically go from like 2 volts over here all the way up to like 2.87 volts up here, right? So very wide, not very tight at all. So this is not going to be one that we actually want to pursue. So then what do we want to do to get a tighter range? So what do we want to do to get a tighter range on our output? Well, remember, we had 3 of those 1N914 diodes. So what we can do is now we can use those diodes as a reference, right, in order to get our 2.5 volts out. So if you remember correctly, the diodes, they had a certain forward voltage drop depending on the current that they had on them. Let's take a look at the data sheet one more time real quick. So now that we know what we're looking for, because what do we want? We want to be able to get, this is just still a voltage follower, right? Buffer circuit. So what we want is, if we want a 2.5 volt voltage reference out here, then what are we going to need? We're going to need a 2.5 volts on this in plus pin right here, right? And in order to get a 2.5 volt reference here, well, if we're using the diodes as our reference voltage, well then whatever current we're going to send down, the equal voltage drop across these three diodes, so 2.5 volts divided by 3 diodes, that comes out to 833 millivolts per diode. So now what we got to do is we got to go to the data sheet and we got to see how much current do we need to pass through these diodes in order to cause an 833 millivolt drop across the diode itself. So let's take a look at the data sheet. So here we have the data sheet. We're going to be looking at figure 5 here. Figure 3, 4, and 5 are all the same information, but the only thing that's variant on it is the forward current and forward voltage ranges, right? So if you look here, figure 3 is it's in the microamp range. Figure 4 here is in the milliamp range, but it goes from 0.1 to 10. And figure 5 here, again, it's in the milliamp range, but it goes from 10 to 800. And then, so we're going to be using figure 5 because we need 833 millivolts. And you can see here the forward voltage on figure 4 only goes up to 750, so we need to come down to this figure 5. So figure 5 we want to go over, we want to find our forward voltage drop, and of course it's logarithmic, right? So 0.8, and we're going to say since this is about 0.9, 0.8, we're going to roughly say that 8.3 is maybe somewhere around here, right? So just as a starting point, we're going to go ahead and say 40 milliamps. Should be about I was saying it needs to be about 40 milliamps. So if you take 11.1, divide it by 40 milliamps, and you get about a 278, 280 ohm resistor. So let me just get that out. So 278 was the common resistor I went with. And again, the min-max is all the same as I explained earlier. So that gives us about a 40 milliamp current draw. And so when we got that current draw, that gives us a VF of about 797. Now, I calculated this. If you want to see how I got this formula, because I eyeballed it on the data sheet, right? We eyeballed this, and we were able to say, oh, okay, I needed 40 milliamps, right? But then after that, in order so I can make a formula so this could be a little more fluid, I needed to be able to get that data. And so I formed the table and I made a chart, and then I had Google Sheets just output a formula for me. If you'd like to see how I did that, leave a comment down below and I'll go into details on how I extrapolated that formula and the data from that chart. But either way, the formula that I got for it was 639 plus 42.9 times the natural log of our current draw. And so that gives us our voltage drop here across the diode, and that's per one diode, right? So remember, we have 3 of these diodes. So the actual output voltage is going to be about 2.4 volts, which is 3 times the diode drop across each of them. And so again, this is just a rough estimate because I'm eyeballing a chart, I'm doing some maths, but we'll plug the simulation in and we'll see how close we can get. If nothing else, all we're going to really do is change this resistor. So we can see here at 11 volts, we get our 40 milliamps drop and gives us a forward voltage of about 800 millivolts per diode, times that by 3, and it gives us about 2.4 volts on it. And of course, we do the same thing for the 9 volts, and we get 236 to 237. And if we go up to 12.6, we get up to 241. So you can see on these going across here, this is a pretty solid. It's because we don't really have any tolerances on this thing, so to speak. And so just the 1% tolerance on the one resistor for the current draw. But you can kind of see here that the current really doesn't change that much. And that little bit of current draw really isn't going to change the voltage drop on our diode that much. So this thing is pretty solid. And when we look at this though, what we want to care about is that range right here. So how tight is this range? Well, we can see here from 9 volts to 12.6 volts, we have a range of about 43 millivolts. So that's definitely within our plus and minus 50 millivolts spec that the boss had given us. So this is a pretty solid methodology to be able to use, right? All we need to do is be able to soak 45 milliamps maximum. And so roughly about 40 milliamps, right, as it goes down. So let's take a look at this on the simulator real quick and see how it looks while we traverse the 9 volts to 12.6 volts. So let's go ahead and run the simulation. And you can see we're going to run it on V4, which is this source right here. And we're still running it just from 9 to 12.6 at an increment of 0.1. We have our set resistor here, 278 ohms. And we have our 3 diodes. So let's go ahead and run that. And you can see with this 278 ohm, we're going from 235, 2.35 up to about 242. And what did my spreadsheet say? About 235 to 242. So this calculator comes out pretty good for what we were expecting. So then what do we want to do? We want to actually change this because we don't want the 242, right? We want to get the 11.1. At 11.1 volts, we want this to actually be 2.5. So now that we know our calculator is pretty accurate, I'm not going to trust it 100%, but let's take this down to about 150 ohms. That gives us about 2.47, right? And then so let's go ahead and take a look at this on the simulator and see what 150 ohms gives us. So we go back to this, move this to about 150 ohms. And then we can see here at 150 ohms, it drops us to about 2.45 all the way up to 2.54. Still pretty good. Definitely within our margin of error, right? From 9 volts, we're still within our spec that we want, which is 50 millivolts plus or minus, because we're only down 45 millivolts here. And at 12.6, we're at 2.548, which is technically below the 2.55 limit. So we're still within plus or minus 50 millivolts that the boss had requested. So this circuit right here with 150 ohm set resistor and the 3 diodes would be a good starting point to go ahead and put this on a breadboard and try out. And it should work from 9 to 12.6 volts. And again, when you get into the real world, you might have to adjust the R14 a little bit, that 150 ohm R set resistor, but otherwise it's looking like a pretty good solid solution. So right here, we could go to the boss right now. We could hand him this circuit and be like, here's using the stuff that you gave me. Here's what I have, and it'll work, right? But let's go one more step further. And what we're going to do is we're going to, instead of using, because right now we have to use something like 55 milliamps in order to bias this circuit, right? In order to get our 2.5 volts out, we need to be able to drive 55 milliamps through these diodes in order to set that pin right there. Can we do this in a way that A, we get a little more functionality, and B, we expend less current needlessly, right? And so can we do this maybe with 5 milliamps of bias current? Then how can we do that? All we got to do now is, instead of just doing a follower, a buffer circuit with that op amp, let's go ahead and use the op amp for some function. And let's go ahead and turn it into a non-inverting amplifier. That way we can take those three diodes and knock it down to 1 diode. And now we can plan for a 5 milliamp draw down through that diode. And then whatever that voltage drop across that diode is, we can just tweak the output with our feedback resistor to give us the output voltage that we want. So let's go back to the calculator again. And so now we have a lot more things that we got to input. We still have our input voltage. We have the number of diodes being 1 instead of 3 this time. ID of 5 milliamps. And then we need to calculate that R set resistor, right? Well, how do we calculate that R set resistor? Again, we're just talking Ohm's law right here. So we know that we start with 11.1 volts. We can just estimate, right, the voltage drop across that diode. We'll just say 0.7 volts to give us something, even though it's probably meaningless to do it anyway, because it's just one. So we could probably just go to ground. Well, we go 11.1 minus 0.7, and then we divide it by the current that we want, which is 5 milliamps, and it gives us about a 2.2K ohm resistor. So that's now our set resistor. Now that we got our set resistor, what is the voltage reference at that 5 milliamps? Well, when we put that 5 milliamps into our calculator, we get about 706 millivolts. And so in order to calculate our gain now, then our gain needs to just be, we're going to start with 0.706 volts. And what do we want to end with? We want to end with 2.5 volts. So then 2.5 divided by 706 millivolts, that gives us a gain of about 3.53. So that's going to be our gain amplification right there. It's 3.53. So if we go back to 11.1 volts, so we got our output voltage, which is just calculated by the gain of the system, which is our input voltage, which is the VF, times 1 plus RF divided by RG. So at 11.1 volts, our output voltage is going to be about 2.49 volts, according to this. And then likewise, if we go down and do 9 volts, we get about 2.42 to 2.49, and 12.6 gives us 247 to 255. So you can see again, we got everything up here. And again, when we look at our range of just choosing one of the columns, we'll take the nominal value here. We can see that our range is 54, 55 millivolts, which is still within our plus or minus 50 millivolts. We're still above 2.45 and we're well below 2.55. So this one right here is also pretty accurate. So let's go now and let's run the simulation. And so when we run the simulation, we're now doing it on V5 with all the same parameters. And we can see pretty much exactly as the calculator came out with. I got about 2.453 up to about 2.508, which is exactly what the calculator pretty much came out with right there. So we could go through the circuit and tweak it a little bit more just by changing R26, but we're within spec right now. And the nice thing about this one is, one, we're only pulling 5 milliamps down. We're only biasing 5 milliamps instead of 55 milliamps. So we're saving power there. And second is this now becomes a more universal voltage reference source. So now all we got to do is, if we wanted to change the voltage reference source, is change the feedback resistor here, that R29. If we change that R29, we can change the gain. And then when we change the gain, we can have any voltage that we want as a reference, not just 2.5, pretty easily and without having to change too much stuff. Whereas in the other one, we would actually be very limited, right? If we have 3 diodes, there's only a maximum output voltage that we can get to. But in this one, our limit really is going to be our VCC on the op amp, right? And this op amp is rated up to 16 volts. So we could feed it all the way up to 12.6 volts, no problem. And we can get a voltage reference anywhere up to pretty close to that. Thanks for watching this episode of Dominic Does DIY. I hope you enjoyed the episode. And if you did, please like and subscribe and share the video. But until next time, have a good day.